Hello, everyone. Welcome to another week of GROOT. Today we'll be hearing from Noah Wisdom about fields in equivariant algebra. So take it away, Noah.
Hello, thanks for having me. So in this talk, I'd like to discuss Tambara functors, particularly a nice kind of Tambara functors. Um, so I'll briefly give a spiel about why homotopy theorists care about these, and then there won't really be any homotopy theory for the rest of the talk. Um, so, uh, so recall, like, ordinary cohomology has this cup product that gives you like this ring structure. And then you can ask for generalized cohomology theories to have similar multiplicative structures. And this leads you to thinking about like coherently multiplicative structures like E infinity rings, this kind of thing. Equivariantly, you can ask what is the analog of an E infinity ring? One possible answer is a G E infinity ring. And then you can ask, well, what ring-like structure does this impose on your homotopy groups? And the answer is that you get a Tambara functor. So equivariant homotopy theorists care about Tambara functors because these are the structure that naturally appears on most of our ring objects, like topological K theory and equivariant topological K theory of various forms, and equivariant cobordism of various forms, being the main examples. So while you can do this, I think you can do this for like general compact Lie groups, something like this. We're going to be working with finite groups. And in particular, later on, we're going to specialize to cyclic groups of order p to the n. So I'm going to start by sort of explaining what is a Tambara functor. And I'm going to start by giving an example of a Tambara functor that that is going to be abstracted. So we start with a finite group. So my example of a Tambara functor is start with a finite Galois extension with Galois group G. So G is acting on a field L, and the G fixed points are K. Well, one of the things that one of the like pieces of data you get from this situation is a collection of intermediate fields. For every subgroup of G, you can form the fixed point intermediate field. So these intermediate fields have restriction maps. They include into each other according to how the subgroups of G include into each other. So it's like a contravariant functoriality from like the partially ordered set of subgroups of G to the partially ordered set of subfields of L. We additionally have norms and transfer maps. These are a little bit funkier. So roughly speaking, at least like the norm from L to K, for example, is given by the product over the Galois conjugates. And the transfer from L to K is given by the sum of the Galois conjugates. So these are no longer inclusions of fields, of course. They're not ring maps. Norms are just multiplicative monoid homomorphisms, and transfers are just additive group homomorphisms. But this fact that the norm and transfer have something to do with this group action is like important. In fact, moreover, there are residual Weyl group actions on each of these fixed point fields, which I'll say a little bit more about. Or I'll say more about what the Weyl group is. So you don't have to like Wikipedia in the middle of me talking. But the point is that there are sort of group actions floating around. L has a G action, K doesn't really have any action. But norms and transfers and inclusions sort of have their formula that relate these things. Yeah, they're compatible in some sense. So a Tambara functor is going to abstract this situation. In a Tambara functor, we no longer ask for fields. We just want a collection of rings for each subgroup H of G. I'm going to sort of convert between the collection of subgroups of G and the collection of transitive G sets, which are necessarily of the form G mod H, the left cosets, for example, of G associate the left cosets of some subgroup of G. So I'm going to ask for a collection of rings for each subgroup of G, and then I'm going to ask for restrictions between them that are not necessarily injective anymore. So if I have a map of G sets from G mod H prime to G mod H, then I'm asking for a restriction map that goes the opposite way. So it's like this contravariant functoriality. And note that you have a map of G sets essentially when H prime is a subgroup of H. Then you have a map from G mod H prime to G mod H. Or there's like a subconjugacy way to say that you have a map of G sets. But I generally work with abelian groups, so I don't have to worry about conjugating things. So I think of this as just H prime being a subgroup of H. And then a Tambara functor has more data than just rings, which sort of contravariantly depend on subgroups of G. We also have norms and transfers. The transfers are just additive group homomorphisms, and the norms are multiplicative monoid morphisms. And they vary covariantly. They are covariant functorial with respect to subgroup inclusions. Now, I notice that I phrase this slightly differently. We have restrictions whenever we have a map of G sets, but we only have transfers and norms when we have an inclusion of subgroups. So the point is that, the point I'm trying to make is that we have slightly more maps of G sets than we do subgroup inclusions. Like, there's only one way to include subgroups, but like there are multiple ways to map G sets. So like the G set G mod E, it doesn't just map to itself by the identity, but you can also translate it. And that's an automorphism of this thing. So my point is that automorphisms of G sets are going to pick up a residual, automorphisms of G sets are going to give us automorphisms of our rings. In particular, the automorphism of a G set G mod H is the Weyl group of H. So it's given by the normalizer of H, quotient by H. And generally, we will be working with abelian groups, or H will be the trivial group. And so this Weyl group will be G mod H, or just G when H is trivial. So in particular, this G mod E, so the rings G mod H, I might say that they're in level. It's the ring in level G mod H, and the G mod E level is the bottom level. I'll try to be careful about not just saying bottom level and emphasize that it's the G mod E level. So the ring associated to the G mod E level is a G ring. It has an action of G, for example. And if G is abelian, then all of our rings have G actions by sort of project, like the G is the Weyl group of everything. So all of our Weyl groups are quotients of G's. So G acts by like restricting along the quotient map, if we wanted to think of it that way. So one of so there are some sort of nasty and ugly formulas that are kind of awful to write down. But the main one that's actually going to be important to us that we will use sort of over and over again is very much understandable from this like Galois example. Namely, if you transfer up from the G mod E level to the G mod H level and restrict back down, then that's given by summing along the H orbits. And similarly, if you norm up from the G mod E level to the G mod H level and restrict back down, that's given by taking the product along the H orbits. So sort of like this formula means that if you understand the group action, then you can get a little bit of control on how the transfer and restriction maps have to behave. Any questions on Tambara functors so far? I'll give some examples. Okay, more examples. So if I have a ring with an action of a group G, then you can consider all of the fixed point subrings. And exactly as in the case of our Galois extension example, all of these fixed point rings give us a G Tambara functor. and it's, at least on my screen, it's cut off, but the notation for this is an underline symbol. So if I have R a G ring, then I get a G Tambara functor underline R. This is actually a right adjoint. It's a functorial construction from G rings to G Tambara functors. It's right adjoint to the construction that sends a Tambara functor to its bottom level, the G mod E level. And I haven't said what a morphism of Tambara functors is. I will. The adjunction unit is like so useful. It's a great gadget. And I'll actually kind of allude to what the adjunction unit is when I say what a morphism of Tambara functors is. Which is, I mean, it's exactly what you think it is, if you think it's anything, probably. Another example, which is a little bit crazier, but is like pretty important. If we have an H Tambara functor for H, a subgroup of G, then we can construct out of that a G Tambara functor. So on each ring, or sorry, on each transitive G set, G mod L, the co-induction from H to G of K is given by evaluating our H Tambara functor on the restriction from G mod L from a G set to an H set. So this is like some complicated, weird thing, and it sort of like miraculously just constructs a Tambara functor. So roughly, what is this doing? So one of the things to note is that if you do this restrict a G set to an H set, you might not have a transitive H set anymore. So you have to extend your Tambara functor. If you have a disjoint product of H orbits, you have to extend your Tambara functor to like be co-product preserving or send co-products to products. So for example, the G mod E, sorry, the H mod E level, the G mod E level of the co-induction from H to G of an H Tambara functor is going to be like a product of copies of the H mod E level of the H Tambara functor we started with. So this co-induction is sort of like, it's sort of heuristically, it's like freely taking products of your rings in the sort of lower levels. And then as you go up, it's sort of reducing how many copies of the product you have. And eventually you're just left with the top level at the very top. So like if you restrict if you take the G mod G, the top level, which is the G mod G level, you restrict that to an H set, it's going to be H mod H. So co-induction sort of preserves top levels of Tambara functors. Co-induction is also a right adjoint. I will almost certainly say this at some point, I hope. Morphisms of Tambara functors. So Tambara functors are neat. And one of the neat things that you can do with, so Tambara functors specifically are thought of as like rings. They're like equivariant generalizations of rings. And what is a very special kind of ring? A field. So you might hope that there's some way to like maybe define ideals and stuff of Tambara functors, and then define a field as something, a Tambara field is something with no ideals. And then you might want to study Tambara fields because it's interesting. I mean, the study of fields is already so interesting. We've got like Galois extensions and Galois theory, and that stuff is like amazing. So you might just want to see what you can get out of Tambara fields. So you can do all this, and to start with, I'll tell you what a morphism of Tambara functors is. It's a collection. It's just a natural transformation of functors. If you think of a Tambara functor as rings that depend contravariantly on subgroups or on transitive G sets. So it's a collection of maps between the rings at each level, and it commutes with all the restrictions, which includes these Weyl group actions. So these are Weyl group equivariant. And then you also ask for the maps to commute with norms and transfers. So then this is enough to define what a field is in Tambara functors. So non-equivariantly, a field is something where if you map if you map from a field to a non-zero ring, then it's in fact an injective map. It's a monic map. It has the left cancellation property, I guess. And in other words, the kernel is always trivial. So Nakaoka defined a field by defining ideals and then saying a Tambara field is something with no non-trivial ideals. Equivalently, whenever you have a map out of from a Tambara field to a non-zero Tambara functor, then that map is injective, left cancelable or whatever. And this is equivalent to the maps at each G mod H level being injective. Nakaoka then, so like this is kind of like annoying to like check. Like it's annoying it would be really tough to like check some property against all possible like maps out of your object. Even if you tried to state it in terms of, even if you were like trying to show that there were no non-trivial ideals of your Tambara functor, ideals are kind of like tough to like work with and compute. Like we don't even, as far as I remember, we don't even know all of the ideals of the initial Tambara functor, like the analog of the integers. We don't even know like all the prime ideals of this for like every possible group, something like this. There's a paper that like gets started on this, which is, it's a good paper. But we want something more checkable. So the first thing that you might try to do if you have a field, or if you have something that's candidate for a field that you want to know if it's a field, is you might look at this adjunction unit I alluded to earlier. And if you look at this adjunction unit, this is non-zero, so it has to be monic. And so if you have a field, all the restriction maps have to be injective, because this adjunction unit that I was alluding to, the map on level G mod H is essentially given by the restriction map. This is relatively straightforward if you unwind the definitions. And then the other condition, there's another property that you need to have in order to be a Tambara field, which is that your G mod E level has to sort of be a field in G rings, is how I've been thinking of this condition. So you want no non-trivial G invariant ideals. And by this, I do not mean that the fixed points are a field. By G invariant, I just mean like preserved by the G action, but not necessarily fixed by the G action. Or rather, this is what Nakaoka means. And then sort of the impetus for what I'm going to spend a good chunk of the rest of the talk talking about was an observation by David Chan and Ben Spitz, where they realized that this point number 2 in Nakaoka's theorem is really just the statement that this G mod E level is a product of fields permuted transitively by the G action. And like this is actually straightforward to prove. You just use the Chinese remainder theorem, and it's like less than a paragraph of proof. And this is equivalent, an equivalent condition. But it's like psychologically, it's like so much, it just feels like you have so much more control over what's going on when you write it down like this. So this is also this result of David Chan and Ben Spitz is why I've been thinking of this condition too as like a field in G rings. Maybe this is like something that's known in the literature. I'm not, you always discover like someone has been thinking about what you've been thinking about in the 90s or something. Any questions on Tambara functors, Tambara fields before we start getting it?
Hi. So the last like observation of Shannon Spitz, like is it written down somewhere or? Or did they just know this?
So David Chan told me this at a random conference, and then it was so useful. I have it written down in the preprint that's going to appear in archive like tomorrow or something. So
all right, yeah, thanks.
And then I will probably at least spend a couple minutes talking about another project which also uses this result, and the proof is also written down there, but that might not be coming out quite as soon. But yeah.
Yeah, that's it. That helps. Thanks.
Examples of fields. Okay. So if you start with a field and you co-induce it, so a Tambara functor for the trivial group is just a ring. I can, if I start with a ring, I can think of it as the Tambara functor for the trivial group, and then I can apply functors to it like co-induction. So if you co-induce up a field, it's still a field. You can check this directly. Co-induction from H to G takes field-like Tambara functors to field-like Tambara functors. These are both checkable straightforwardly with Nakaoka's theorem. Also, this co-induction from the trivial group to G is like not very opaque. By which I mean it's not like tough to understand. So this co-induction from E to G is given in the G mod E level by just functions from G to your thing, to your ring or field in our case. And then it's G acts, so it's a copy, it's a bunch of copies, products of your field, and it's you have a copy of your field for each element of your group, and then the group just permutes those copies freely and transitively. And then the co-induction from E to G is just the fixed point Tambara functor of that G ring. So that's nice. So like in each level, it's like a product of copies of your field, and they're sort of permuted transitively, at least by the Weil group. Maybe also freely. Something like that. And in particular, the G mod G level is just the field you started with. Another way you can get a field is if you start with a field, you give it the trivial action and form the fixed point Tambara functor. So the restriction maps are all the identity maps, but the norms and transfers are not quite the identity maps. They're like they're sums over appropriate orbits. So they end up being like multiplication by integers or raising to integer powers. This is like the field this is the construction that equivariant homotopy theorists love to work with, as far as I can tell. Most computations I see people doing, not that I deep dive into equivariant computations, but a lot of them seem to be like, start with F2, the field with two elements, and then give it the trivial action, and then do a computation with that. But there are a lot more fields, as we shall soon see. There are a lot more fields than just these. So I think there are a lot more computations people could be doing that would be interesting. I haven't extensively searched to see if people have actually done these yet. But one more example, which is really weird. It's sort of like the most pathological, one of the most pathological examples that we can see. And by pathological, I mean not of the first two forms. Co-induction and fixed point Tambara functors feel understandable, but this one feels less understandable. So we look at the cyclic order P group, and then define the CP mod E level of our Tambara functor to be the field FP rational functions in T. So this is just the important part is that this is an example of a non-perfect field. And then I'm going to take the top field, the CP mod CP field, to be the image of the Frobenius map. Then the norm I'll take to be the Frobenius map. It has to be the Frobenius map. essentially. Well, so long as the restriction map is an inclusion, which is sort of, as we'll see, it sort of has to be, or I guess it turns out that it sort of has to be, it has to contain the image of Frobenius because the norm map sort of has to be Frobenius. Oh, I'm giving this the CP mod E level, the trivial CP action also. And then the transfer is forced to be 0 by the double coset formula, and the norm is forced to be Frobenius by the double coset formula. So I guess the point of this example is that we can write something down which is visibly neither co-induced nor fixed point field associated to the G action on the G mod E level. It's neither of these. And roughly speaking, this is the only thing that can happen. So it's not a coincidence that the characteristic of our field also divides the order of our group. Yeah, when the characteristic is co-prime to the group, then you can only get fixed point Tambara fields, at least for C p to the n. But I'll explain why this is. So the goal now, the double coset formula, along with Nakaoka's theorem that says that all restriction maps have to be injective, like this is enough to just classify all of the CP to the n Tambara fields. We can just give a recipe that like constructs all of them, and then it's straightforward to distinguish them, I think. Relatively straightforward. At least it's a problem for like group theorists and number theorists, if there is any ambiguity, which I don't think. Anyways, the important part is that we can like build all of these Tambara fields, CP to the n Tambara fields. So the first thing to do is this result of David Chan and Ben Spitz that says that our G mod E level of a Tambara field is a product.
I'm sorry, but there's a question in the chat. If you're...
Do norms of Tambara functors send fields to fields? Not necessarily. That's sort of the weird fact. So the norm sends oh, you mean the norm as in like the induction, perhaps? In that case, I'm not sure. If you meant like the norm as in the level-wise map, that does not necessarily send fields to fields. If you like had bottom level of field, the image of the norm might not be a field. That only happens in characteristic P because Frobenius is a field map. I hope I answered your question, but if I didn't. Okay, induction. Yeah, I haven't thought about induction. That would be interesting. Especially to see how it plays with the classification that we're about to see. Right, so this David Chan and Ben Spitz result that the G mod E level of a Tambara field is a product of fields. You can write this suggestively as like a co-induction thing. So if I have a product that's like not trivial, then I'm going to call my Tambara functor separated. And if my product was just one field, if I was just co-induced from a G field, a G ring, which was whose underlying ring was a field, then I'll call my Tambara field pure. I'm workshopping these names. I'm like open to changing them. But I don't know. I thought separated because like the Zariski spectrum is disconnected or something, but doesn't matter so much. So when we want to classify CP to the n Tambara fields, the first step is going to be to reduce our classification to the pure fields. So we want to give a recipe that constructs all separated Tambara fields in terms of pure ones. So for CP to the n, if we have a separated thing, then it's actually co-induced from a pure thing. and I will give you a proof in a special case that sort of has the flavor of the full proof. I think this is true. I've been talking to David Chan a little bit about this. I hope this is true in general, but it's like not as straightforward to prove this in general. At least I hope for abelian groups that this kind of theorem is still true. So in particular, this bottom level, like this G mod E level structure is actually telling you something about the entire structure of the Tambara functor. It's giving you like comprehensive information. So a special case of this is that if the G mod E level of our Tambara field was actually just functions from G to F, so sort of maximally separated, then our Tambara field is just the co-induction of that field. And notice that it agrees with the co-induction on the G mod E level. In both cases, it's functions from G to F with the corresponding G action. Products of copies of F permuted transitively by the G action. So I'll give you the proof of this special case that is sort of the idea in general. So you use the double coset formula. So restriction maps, if you look at just the restriction of the restriction map to the fixed points, and you restrict up and then if you restrict the transfer map to the fixed points, transfer up and then restrict down, the double coset formula forces this to just be sum over certain orbits. And in particular, you can, the precise way that it is sum over orbits, you can use to just construct, show that you can, given any element in the H fixed points of K of G mod E, you can construct an element that transfers up and then restricts back down to that thing. My point is that the restriction maps are surjective maps from the G mod H levels to the H fixed points of the G mod E level. Well, the restriction maps are also injections, so that means they're isomorphisms. And that precisely says that that K is isomorphic to the fixed point Tambara functor associated to its G mod E level viewed as a G ring. In other words, K is isomorphic to this co-induction. And this kind of idea is like, we just hammer this idea throughout like the whole, this whole like classification argument. We use this over and over. The fact that to show that a restriction map is, to identify something as a fixed point Tambara functor, all you have to do is show that restriction maps surject onto the fixed points because they're already injective for free. And the double coset formula like will oftentimes force surjections. Any questions? So I didn't write this in the theorem, but in fact, you're co-induced from a pure thing. So this actually reduces our classification to just pure CP to the n Tambara fields. Right. So also note that this corollary does not require CP to the n. This works for any group. And I will actually use it when I'm talking about this other project in the last like 5 minutes. Okay, so we can, towards classifying CP to the n Tambara fields, the first thing to note is that if you have a pure G Tambara field, and the characteristic of the G mod E level doesn't divide the order of the group, then you had to be a fixed point Tambara field, which is like, that's like an enormous amount of structure that's forced. Like this classifies like most Tambara fields right out of the bat, right off the bat, like, and it's a very similar game. So I'll give you the, and in particular for CP to the n Tambara fields, this will give us a complete classification except when the characteristic is P. So how do we argue this? Again, it's enough to show that the restriction maps are surjective from the G mod H level to the H fixed points of the G mod E level. And how do we show they're surjective? We use the double coset formula. So you start by transferring from the G mod E level to transfer something in the H fixed points of the G mod E level to the G mod H level. And then you restrict back down. Because it's fixed by H, the sum over the H orbits is just going to be sum of order of H copies of X. So you transfer up and restrict down, and you just get order of H times X. Well, our assumption implies that this is just a unit multiple of X. And this is enough to deduce that the restriction map actually was a surjection. I mean, if you transfer and restrict, that's a surjection. So that means the restriction itself had to be a surjection onto the H fixed points. And this gets you an isomorphism that you need. So this canonical map, this adjunction unit from K to the fixed point Tambara functor of its G mod E level. In level G mod H, it's given by the restriction map from K of G mod H to K of G mod E, observing that the fact that this map is, the equivariance of this map forces the image to land inside the H fixed points. I don't think I said that already, so yeah. Right. So this is repeating. Restriction maps are injective. So it was enough to show that they were surjective. So all we have to do now is classify pure fields of characteristic P for C P to the n. And I don't know, I haven't even begun to think about how crazy things can get for groups that are not CP to the n. Especially one of the things that seems like it could go weird is if you have the order of your group has distinct prime factors, because our argument is still going to give us some control over what happens in our Tambara functor, but it's not going to it's no longer going to completely control the entire behavior, especially at sort of subgroups that are whose index or order is divisible by the characteristic of the field. Okay, towards classifying pure CP to the n Tambara fields of characteristic P. So the first thing that we can observe is that you can actually build all of these just out of CP Tambara fields in a relatively straightforward way. And this is actually, I think, true quite a lot more generally. We didn't really need the pureness, I think, and we didn't really need I think this works just on the level of Tambara functors. We didn't need pureness and we didn't need the characteristic p-ness. But at least the way that it's built up feels a little bit more graspable in the pure characteristic p case, I suppose. But I won't get too much into this. I'll hand wave this part. But so this reduces the classification now to what can happen for CP Tambara fields. So our example before of this weird Frobenius thing essentially controls, this gives the prototype for what can happen in one of two cases. So if you have a pure CP Tambara field of characteristic P, then CP either acts trivially on the CP mod E level or it does not. If it acts trivially, then the CP mod CP level, this can be any subfield of the CP mod E level, which contains the image of the Frobenius map. Any choice of subfield gives you a Tambara functor, and any distinct choices, roughly speaking, will give you distinct Tambara functors. And I say roughly speaking because it's not completely true, but like non-isomorphic subfields. I guess would be enough. So this tells you how to get, in one of two cases, this tells you how to get all possible pure CP Tambara fields of characteristic P. And then the other case we have to handle is, what if CP does not act trivially on the bottom level, the CP mod E level? So for this, we use Art and Schreier theory, which kind of, I don't know, comes a little out of nowhere to me, but I'm really excited that I get to use Art and Schreier theory for something. As an algebraic topologist, there are not many chances for me to use Art and Schreier theory. So if it acts non-trivially on this field, CP mod E level field, then the inclusion of fixed points is an Art and Schreier extension. It's a Galois extension with Galois group CP. So in particular, it is the quotient of a polynomial algebra in one generator by an Art and Schreier polynomial, x to the p minus x minus alpha, where alpha is some fixed point by the CP action. In this case, we can also say what all of the possible behavior is. So for p odd, if p is odd, then the CP mod CP level can be any subfield of the CP fixed points, which contains the image of Frobenius as before, and additionally, it has to contain alpha. If you meet those criteria, then any choice that meets those criteria will give you a CP Tambara field. However, if P is 2, then you get, so why do you have to contain alpha? Because alpha is the norm of X, right? The double coset formula forces the norm of X to be the product of the CP conjugates, the CP orbits of X. This is just the constant term of the polynomial x to the p minus x minus alpha. It's alpha. So this containing alpha condition is just saying you contain the image of the Frobenius is part of what you have to contain the image of the norm, and containing alpha gives you the rest. So if you contain both of those things, then that means you contain the image of the norm, like you're actually a well-defined Tambara functor. And the transfer is forced to be 0 by the double coset formula, and the fact that the transfer of x is the coefficient of the x to the p minus 1 term. When p is odd, this coefficient is 0. The transfer is an additive homomorphism, so that's enough to say that the transfer completely vanishes. However, when p is 2, the x to the p minus 1 term is minus 1. It's no longer 0. So now the transfer is not necessarily going to have is not going to be the 0 map. In particular, give me any a in the CP fixed points. What is the transfer of ax? Well, it's going to be minus a, because it's the sum over the CP conjugates, and so you can pull a out of that sum, and so you get the a times the transfer of x, which is minus 1. So that the transfer of ax is minus a. A is an arbitrary element of the CP fixed points. So all of a sudden, when p is 2, you actually have the transfer is going to just recover the entire image of the CP fixed points. So in fact, there is no choice when p is 2. The CP mod CP level has to be the entire CP fixed points of the CP mod E level. So when C2 acts non-trivially on the bottom level, in that case, there's you actually have to be a fixed point Tambara functor for p equals 2. So this is like the very last thing I figured out in this work, and this I was like, oh my gosh, this is it's just so cool that there's different behavior for odd primes versus even primes, even prime. I don't know, that it just is, it's exciting. I really like that. And also this finishes our classification. Any questions before I move on to the last topic? Maybe to sum up, the classification is to get any CP to the n Tambara field, you start by observing that it's co-induced from a smaller thing, whose bottom level is a field. In almost every case, that smaller thing is going to be a fixed point Tambara field associated to a group acting on a field. If that field has characteristic P, then you have to build it out of CP Tambara fields. And all of the CP Tambara fields have this form. One of either of these, split into these two cases. They're one of these two things. So that's nice. I mean, like the overwhelming majority of Tambara fields are just fixed point Tambara fields. I don't know. That's like kind of, it's weird that they're not all fixed point Tambara functors, and but it's like weird that so many of them are. Okay, so next, this for the last like 4 minutes or so, I'm gonna just like tell you the main result of a different project on Tambara fields that I worked on with Ben Spitz and Jason Schuchardt. So this concerns the question, what do algebraically closed fields look like? So Burklund-Schlank-Yuan have this amazing paper, the chromatic Nullstellensatz, and they classify the algebraically closed, well, Nullstellensatzian fields in like Tn local commutative rings or something. So that's like amazing. But also this begs the question, what are algebraically closed objects or Nullstellensatzian objects in other settings? I use these words interchangeably. Alan Yuan yells at me when I do this, but people have assured me it's at least okay for Tambara fields to use them interchangeably, I guess. So a Nullstellensatzian object is an object where every compact algebra has a section. So in ordinary fields, a compact algebra over a field is just a finite polynomial, a finitely generated algebra. And a section is just a choice of root of a collection of polynomials, a choice of roots of polynomials. So an ordinary field is Nullstellensatzian precisely when it's algebraically closed, because all polynomials have roots. And the theorem that I prove with Ben Spitz and Jason Schuchardt is that a Tambara functor is Nullstellensatzian if and only if it is the co-induction of an algebraically closed field. In particular, its field like I don't know, this is like, I mean, it's neat. It's cool that like we were expecting to get like, so like one of the things you might guess is like you take algebraically closed field, like the complex numbers, and you take the constant Tambara functor associated to that. Our guess was that that was going to be algebraically closed, Nullstellensatzian. And it turns out that it's not. So this is like cool. Like one of the things that I was alluding to earlier, but to me, this suggests that as equivariant homotopy theorists, we need to do a lot more computations with co-inductions of fields. Like clearly they are important because they are constructing all Nullstellensatzian objects. And there's another reason that I think co-inductions are important that I'll say. So proving this, we use the polynomial algebras of Blumberg and Hill. These sort of let you talk about polynomials. So here's another result. The category of Mackey functor modules over a co-induction is equivalent to the category of modules over the thing you started with. Well, who cares about categories of modules? K-theorists. So if you define equivariant K-theory of a Tambara functor, people are working on this. Like Mona Merling has a version for G rings, I think, and I believe I learned from David Chan of a project that is trying to compute or trying to construct K-theory spectra of like GE infinity ring spectra, which would include Tambara functors. I don't know precisely the state of the art on this, but heuristically, equivariant K-theory is going to be built out of some category of modules. Well, if you start with an algebraically closed Tambara functor, then its equivariant K-theory by this theorem is just determined by the ordinary K-theory of the algebraically closed field you started with, heuristically at least. So that is like one other reason that you might care about classifying the Nullstellensatzian Tambara functors. Yeah, that is all I have to say. Thank you for coming.
Great. So let's thank Noah for a wonderful talk. Applause in the chat. Yeah, does anyone have any questions for Noah? So if not, I will go ahead and stop the recording.